In continuation to our previous lecture, we will continue to build or develop the concept based on rolling loads and influence line. So in the previous lecture, we saw the definition of rolling loads. We defined rolling load as those live loads which change their position. And by common sense, we can say that when load change their position, the value of stress function also change. The load position which cause maximum effect is known as critical position, and as a designer or a structural engineer, we are concerned about critical position. In this lecture, we will see that using ILD, we will find the critical load position for maximum shear force and bending moment at various sections. It may cause maximum negative or positive shear force at a section on beam or a girder. So influence line diagram, as we defined it, as a line diagram which represents to some scale the variation of stress function in a member or a system when a unit load crosses it. So the stress function can be reaction, shear force, bending moment, axial forces, etc. We also see that influence line for statically determinate structure is linear. So let us see, this is a simply supported beam of span say L, and ILD for RA would be like this. On at A will draw an ordinate of 1, ordinate 0, and will join it by a straight line. And similarly for ILD for RB, at B will draw an ordinate of 1, and at A will draw ordinate of 0. So let us see how it works. So we know that the value of a stress function, so this ILD is for RA, so the stress function of this ILD is RA, so the ordinate will give the value of RA for various load positions. Suppose the load is at this point, so at corresponding to this, the ordinate in the ILD will give you the value of RA. So now we'll see that a critical load position for various types of loads. We'll start with concentrated load. So this is an ILD for RA. How we can see that? How we can say that? So the ordinate at A is 1 and at B it is 0. What I will do, I will write it as 10 by 10. So this distance, total distance is 10. So this ordinate is going to be 9 by 10. So if we measure the length from this side, the ordinate is 8 by 10. Now this length at point 3, it is going to be 7 by 10. So likewise, we can find the ordinates at various places. Now if the load is at this point, at point 4, this ordinate will give the value of RA. Now suppose we move the load from other point, from this point to other point, so the ordinate under this ordinate will be equal to the value of RA. So we can say that value of RA is 3 by 10 when load is at this point. So by drawing a single ILD for RA, we can find the value of RA for various load position. Now similarly we will see it. Similarly we will see it for RB. So how we draw the ILD for RB? First we'll draw a straight line. On this side at B we'll draw on ordinate 1. On A side we'll draw 0. We'll simply join it. In place of 1, what I have written? I have written 10 by 10, and subsequently I have written 9 by 10, 8 by 10, 11 by 10. So suppose load is at this point, at point 4. So what will be the value of RB? Because this is the ILD for RB, so it will give the value of RB only. So the value of RB is going to be equal to this ordinate. It is equal to 4 by 10, that is 0.4. Now if load is at this point, it is at the supported side. So the value will be corresponding ordinate. So what is the value? It is equal to 1. So the value of stress function is equal to the ordinate of the ILD corresponding to the load position. So if the load is here, this is the corresponding ordinate, and if the load is here, this is the corresponding ordinate. So critical load position for maximum value for RB. Where will be the maximum value of RB? When the load is at support itself. When load is at B only, then we are going to have maximum value of RB. So just by looking at this ILD, we can say that the maximum ordinate is at B. So the maximum value of RB is going to be only when the point load or the unit load is at section itself or at support itself. Now using the application of ILD, what we do, we assume a load, suppose a van, and on the front wheel load is W1 and on the rear wheel the wheel load is W2. The value of RB using ILD will be W1 means the value of load into corresponding value of ordinate value. So this is the ordinate. So load into ordinate. So value is W2 into ordinate. What is the value? 4 by 10. Since the span I have considered is 10, so this height is going to be 1 for ILD of RB. At B we have to draw 1. So in place of 1 I write 10 by 10, and subsequently I write 9 by 10, 8 by 10, 7 by 10, 6 by 10 like this. So I got the value 2 by 10 and 4 by 10. Suppose we add one more load. Now 4 loads are acting in the beam and we are interested to find the value of RB using ILD. So what we do, simply multiply W3 with the ordinate and W4 with the corresponding ordinate 8 by 10. So now we will draw ILD for shear force at any section C, and Z, that means position of section from left support is 8. So this is our section. How we draw ILD for shear force at C? First we draw a straight line, then we draw a negative part that is equal to minus RB, then we will go on the positive side and draw ILD for plus RA. This is what we will get. So what is this distance? It is 8 from the left support. So we will draw it as 8 by 12. Total length is 12. So this value is 8 by 12. And mind you, this is negative. And for positive shear force at section, what we do, we draw this length will be 4. So this height is going to be 4 by 12. So again using the same concept, this is 8 by 12. So subsequently I will reduce it to 1 by 12, 2 by 12, 3 by 12 and so on. And similarly on this side, this is 4 by 12. So 3 by 12, 2 by 12 and 1 by 12 by using similar triangle. Similarly, if I want to draw an ILD for shear force at C, this is the section. So how we will draw this? First we will draw the negative ILD, then we will draw the positive one, and ordinates we calculate basically. So now we are interested to find the value of shear force at any section. So suppose load is at this point. So at the section there are two values. At the point C there are two values, one positive value and other is negative value. So we'll write that maximum positive shear force at section C is when the load is just right of the section, and it will be equal to 4 by 12. And suppose load is at the section and we are considering it just to the left of the section, so the load will fall on this portion which is negative, that is maximum negative shear force will be minus 8 by 12. Again, suppose the load is at the section, so maximum ordinate we are getting here only. This is maximum positive value and this is maximum negative value. So suppose we want to find maximum negative shear force, then the load should be on the left of the section, and suppose we are interested to find the maximum positive value, the load should be on the right of the section. So we can conclude that critical load position for maximum negative shear force will be when load is just left of the section. So whenever we take section, on the left hand side there is negative value. So when load is just left of the section, it is called as negative shear force, and when we consider the positive part, that is just right of the section, it will give you the value of maximum positive shear force at section C. Suppose we want to draw ILD for bending moment at any section. First we will draw a straight line, then we will draw a hill or a hut like this. So this distance is how much? This is 8 and this is 12 minus 8, that is 4. So this part is 8 into 4. So what is the height of this ordinate? 8 into 4 by 12. So we'll get this. Similar triangle. So this height is 2.6 and this base is 8. So how you will find the value of this ordinate? How you will find? It will be 2.6 divided by 8 into this distance, say x. You put the value of x. So this is the general equation if you want to find ordinate of this. So total height by total base into this distance x. So likewise you can calculate all the ordinates, and on this side the slope will be different because this is 2.66 and this length is 4. So the slope will be 2.66 by 4 and this distance will measure from support. This distance will be x. Similarly, if I want to draw bending moment, ILD for bending moment at C, so the hut will be at the section itself, and this ordinate will be, the length is 3 meter on this side, 12 minus 3, 9 on this side, total length is 12. So it will be 3 into 9 by 12, it is 2.25. So now using the principle of similar triangle, we can find the ordinates. So what will be the value? 2.25 divided by 3 into x. You simply multiply the distance measured from support, you will get the value of ordinates. From this side the value will be 2.25 divided by 9 into x. X is always measured from support. So suppose if we want to find the ordinate of this, so 2.25 total height by total base by 9 into this distance x. If load is here, the bending moment at C will be equal to this ordinate. So as the load moves towards this section, value of ordinate increases. So we can say that for maximum bending moment at any section, the load should be at this point only. So we can conclude that critical load position for maximum bending moment is on the section itself. We apply our ILD to calculate the value of bending moment at C. So these are the 4 loads, W1, W2, W3 and W4. How we calculate bending moment at C? So this is the ILD for bending moment at C. So it will give you value of bending moment at C only. Every point in this ILD is giving the value of bending moment at C only, right? So first load is W1, corresponding to that this is the ordinate. So how we calculate this ordinate Y1? So we know that this total height is 2.4 divided by 4 into this distance is how much? This is 2. So Y1 is equal to 2.4 by 4 into 2. It will be equal to 1.2. What about this length? So how we got this value 2.4? Simply product of Z into 4 into 6 divided by 10, we got 2.4. Now for this W3, the ordinate would be this one. How we find this value? So this distance is, so this is 4. So what is the slope? 2.4 divided by 6 into 4. So 2.4 divided by 6 into 4, we'll get the value as 1.6. For this ordinate, how we'll calculate? 2.4 by 6 into this distance. This is 2. So 2.4 by 6 into 2. So simply we'll put the value. W1, W2 will be given in the numerical. So simply put the values and we'll get the bending moment at C. Now let us try to find the value of shear force at any section C using influence line diagram. So section is at Z is equal to 8. Z we measure from this side. So this distance is 8. So this is the section. Now we want to find the shear force at C. For that we will draw ILD. So ILD for shear force at C will be, this distance is 8. So this is 8 by 12 and this part is 4. So this will be 4 by 12. So first part is negative, the next part is positive shear force. Now there are 4 loads. So we have to multiply this with the ordinates. So W1 into this ordinate W2 into corresponding ordinate, this is 4 by 12, and W3 into this ordinate, and W4 into this ordinate. These three, the Y1, Y2 and Y3 are negative ordinates because they are on the negative side of the IND, whereas load 4 is on the positive part of the IND. So we'll put Y1, Y2, Y3 as negative value, and eventually we'll get the value of shear force at C. We will take one more example. Suppose now the section is not here, the section is at C. This is the section. So this will be our ILD for shear force at C. This distance is 3, so this height is 3 by 12, and the remaining length is 9. So this height will be 9 by 12. So now we have to multiply this load into corresponding ordinate. So this ordinate will be minus 2 by 12. For W2 it will be plus 8 by 12. For W3 the ordinate will be plus 5 by 12, and for W4. Now we'll come to UDL. We'll start with reaction again. We have done with the point load. Now we'll come to UDL. In case of UDL, we have two cases. One is longer than span, the other is shorter than span. To get the value of RA from the ILD, we have to multiply the intensity of load, that is W, intensity of this UDL, into the area under the UDL. So the portion of the UDL that is covering the ILD should be multiplied with this intensity of load to get the value of the corresponding stress function. So in this, the entire portion is covered with the UDL. So RA will be W into A. So what is W? It is the intensity of load. What is A? A is the A. So suppose the UDL is not covering the entire portion, only this part is there, so we have to consider this area only. For maximum value of RA for UDL longer than span, UDL should cover the entire span. Only when the UDL has covered the entire portion, then only we'll get the highest value of area, then only we'll get the maximum value of RA. There are basically two types of load we considered. One is point load and other is UDL. So when we were considering point load, it will be multiplied with the ordinate, and when we are considering the UDL, it should be multiplied with the area. So basic logic we used is, for maximum value, the ordinate should be maximum. To get the maximum value of the stress function, it should be multiplied with the highest ordinate value, and when we are considering UDL, it should be multiplied with the largest possible area. Similarly, we will do it for RB. So how we draw the ILD for RB? So this is our ILD. So entire area is covered with the UDL. So the value of RB is nothing but intensity. This time we have taken 2. And what is the area? Area is half base into height. So base is 10 and height is 1. So value of RB will be 10 kN. So this is another application of ILD for UDL. For point load, we are multiplying with the ordinates. For UDL, we are multiplying with the area under the UDL. So what is the critical load position for maximum value of RB? Again, it is the same, that UDL should cover the entire portion. If entire portion is not covered, then we will not get the maximum area from the UDL. Now moving ahead, now we will come to UDL shorter than span, and we are still considering critical load position for RA. So this is our beam, simply supported beam, and only a portion, that is from 0 to 7, the member is subjected to UDL. Load is moving, suppose load is moving from left to right. So what will be the ILD for RA? It will be 1 on this side and 0 on the other side. So what is the intensity? Intensity is W. And what is the area under the UDL? It will be this portion only, up to this portion, like this. So we have to multiply the intensity of load with the area. So area of trapezium will be h by 2 into sum of parallel sides. This ordinate we can find by similar triangles. So this height is 1 by 1, so we write as 10 by 10. So this distance is 3. So this height is going to be 3 by 10 from similar triangle. So the sum of two parallel sides is 10 by 10 plus 3 by 10, and the distance between them is 7. So 7 by 2 into sum of parallel sides. So we'll get the area, and we'll simply multiply with the intensity. We'll get the value of RA. More area is towards this part, and less area is on the other corner. So we can say that if load is traveling from left to right, the tail of the UDL should be at the support. So entire load should be on the left hand side near support A, and maximum value of RA will get when the tail of the UDL is at A. Now likewise for RB, this is ILD for RB. So we are placing the load towards B because more area is on this side as compared to this triangle. Value of RB is equal to intensity of load into area under UDL. So area is trapezium. So this total length is 10. So we'll write 10 by 10. This distance from the support is 4. So this will be 4 by 10. So and the distance between them is 6. So we'll write 6 by 2 into 10 by 10 plus 4 by 10. So the critical load position for maximum value of RB for UDL shorter than span is when the head of the UDL is at the support. For RA it was tail of the load at the support. Now for RB it is head of the load at the support. Now we come to maximum negative shear force. So as we see that this is the section in the simply supported beam, and this is the ILD for shear force at the section. Smaller ordinates are there. As we move towards the section, the height or the ordinate value is increasing continuously. From support, at support it is 0, and towards the section the value is increasing, and at this point at this section we have two values. One value is maximum on the negative side and the maximum value on positive side. So in order to find maximum negative shear force at a section due to UDL shorter than span, the maximum area should be covered on the negative side. Suppose some part is on the positive side, so it will reduce the shear force, negative shear force, because this part will be positive and this part will be negative. What is the formula? We'll use intensity into area. So area is triangle in this case. So we can say that for maximum negative shear force, the head of the UDL, this head of the UDL should be at the section. Suppose the UDL is up to this point only. So if the UDL is up to this point only, then we'll consider intensity into this area only, and maximum value of negative shear force we'll find when the head of the load is at the section. Again, suppose this load is moved to this part. So what will be the ILD for shear force? This distance is 8. So this will be 8 by 12. Remaining distance is 4. So this will be 4 by 12. And area under the UDL will be the trapezium. So shear force at C, maximum negative shear force at C, will find when the head of the load is at the section. Now this is for maximum positive shear force. So this is the section at C. So this is the ILD which we are using. For maximum positive shear force using ILD, we know that entire UDL should be on the positive side. So for maximum value, the tail of the load, tail of the UDL should be at the section. So suppose load is moving from left to right. So first thing is that entire load should be on the right hand side of the section where positive shear force is there. And to get the maximum value, the tail of the UDL should be at the section, so that we get entire area under this portion. So this is the area of the maximum positive shear force. So now we will come to bending moment. ILD for bending moment with subjected to UDL greater than span. So this is our section, so we'll make a hut or a hill at this section like this, and this ordinate we get by multiplying z into L minus z by L. So what is z? Z is 8, this is 4, so 8 into 4 by total length 12. Now this ordinate is 2.66. So now we know that using ILD we can calculate the value of bending moment at C. So for UDL it is intensity of load into the area covered by the UDL. So this is the UDL, and we see that entire area is covered with UDL, so we'll multiply the entire area. This is the triangle, we'll multiply half base into height, we get the. So what we can say, the critical load position for maximum bending moment at C is that UDL should cover entire span. Suppose it is not covering the entire span, so whatever portion it is covering, that portion we have to include in the area. And one good thing is, in case of shear force at any section, we had two values, positive value and a negative value. But in bending moment in simply supported beam, we see that the entire diagram, that is ILD, is on the positive side. So no need to calculate positive or negative, or no need to get confused also. Now we have UDL shorter than span, so we have to apply our ILDs. So first thing is, we will draw the section, then we'll draw the ILD for bending moment, and then we have to consider the area. We have to consider the area that is under the UDL. So this portion from tail to head of the UDL, we will consider this area. For simplicity, we'll divide this composite area into two trapezium. So this area we'll call as A1, this area we'll call as A2. So the total area will be A1 plus A2 into intensity of load W. So what will be the load position? So how to get the maximum area under the UDL? This is possible when these two end ordinates are equal. So when y1 is equal to y2, so UDL should be so arranged that y1 is equal to y2, then only we'll get the maximum bending moment at C for UDL shorter than span. So let us try to understand this numerical or with some value easy to understand. So suppose this is a simply supported beam of span 12 meters, and we are interested to find bending moment at section C, which is at a distance 8 meters from the left support. So this is the ILD for bending moment at C. Now a load of UDL of shorter than span of intensity 2, and the total length of UDL is 5. So the length of the span is 12 meters and length of UDL is 5 meters. So it is a case of UDL shorter than span. Now this UDL is crossing the this girder or bridge. So for various portion of the load, there will be corresponding area from which we can calculate the bending moment at C using this ILD. But we are interested to find the maximum positive bending moment at C. So since the entire ILD for bending moment at C is positive, so it is irrelevant if we write positive here, because all the values will be positive only. So now we want to adjust this load such that we get the maximum bending moment at C. So how we do that? This is the section Z. It will divide the UDL, this UDL which is of 5 meter, into same ratio as it divides the span. So total span is 12. So this part is 8, this part is 4. So it will divide the UDL also in the same ratio for maximum bending moment. So we can write from ratio proportion, A divided by Z is equal to 5 minus A, that is total length of the UDL minus this part, 5 minus A by L minus Z. So when we cross multiply and solve it, we get value of A. This value is 3.33 and this will be 1.67. Now for this load position, we will have y1 and y2 both will be equal. The ordinates will be equal. So the value of this ordinate y1 will be, from ratio proportion we can find that this ordinate is 2.66, this length is 8. So 2.66 divided by 8 into 8 minus 3.33. So this length is A we calculated as 3.33. So this length is going to be 8 minus 3.33. Similarly, we will calculate y2. So y2 will calculate from this side. So 2.66 divided by total base, that is 2.66 by 4. And what is this length from support to this ordinate? It is 4 minus 1.67. So like this we will get the value of y1 and y2. We already know the value of y0. So we'll substitute these values here, y1, y2 and y0, and we'll get the value of area 1 plus and area 1 and area 2. Simply we'll multiply with the intensity of load, that is 2. Then we'll get the maximum bending moment at C.